March 19, 1945. A muddy field outside Remagen, Germany, 3 kilometers east of the Ludendorff Bridge. Oberfelwebel Karl Hoffman of the 3rd Panzer Division's maintenance company stood motionless before a captured American tank, his breath forming clouds in the cold morning air. The tank bore white stars on olive drab paint, battle scars across its hull, and German kill markings hastily applied by its previous captors, who had seized it 2 days earlier, during a brief counterattack. This was an M4A3E8 Sherman. The Americans called it the Easy 8. German intelligence had warned about improved Sherman variants appearing in late 1944, but seeing one intact and operational presented an opportunity that Hoffman's superiors could not ignore. They ordered a complete mechanical evaluation. What German engineers would discover over the next 72 hours would fundamentally challenge everything they believed about American engineering philosophy and German technical superiority. The examination would reveal not crude, mass-produced machinery, as German propaganda had taught them to expect, but a sophisticated integration of automotive technology that German industry, for all its vaunted engineering excellence, had failed to achieve in any production tank. The discovery centered on something deceptively simple: an engine, not a purpose-built tank power plant like the Maybach engines that powered German Panzers, but a modified commercial truck engine, a Ford GAA V8 producing 500 horsepower. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The context surrounding this encounter requires understanding where both nations stood in March 1945. Germany faced total military collapse. Soviet forces were grinding westward from the Oder River, less than 60 kilometers from Berlin, American and British. Armies had crossed the Rhine at Remagen on March 7th, establishing a bridgehead that would prove impossible to eliminate. The German army, once the most formidable military machine in Europe, was disintegrating. Fuel shortages paralyzed armored units. Spare parts had become unobtainable luxuries. Even when tanks remained mechanically sound, they sat immobilized for lack of gasoline. The Ruhr industrial region, Germany's manufacturing heartland, was being systematically encircled by Allied forces. Production of replacement vehicles had collapsed to fractions of monthly requirements. By March 1945, German panzer divisions existed primarily on paper. Authorized strength meant nothing when actual operational strength hovered between 15 and 30% of establishment. The psychological burden on German forces was crushing. Soldiers who had conquered Poland in weeks, defeated France in 6 weeks, and driven deep into Soviet territory, now found themselves retreating on all fronts. The weapons that had made German forces seemingly invincible in 1940 and 1941 had not fundamentally changed, but the strategic situation had transformed completely. German tankers in March 1945 operated equipment that was often superior to Allied tanks in armor protection and firepower, yet they were losing catastrophically. The cognitive dissonance this created was severe. How could technically superior weapons fail to prevent strategic defeat? The answer lay in factors German military culture struggled to acknowledge. Logistics, industrial production capacity, operational sustainability, and strategic resource availability mattered more than individual weapon specifications. But these were precisely the domains where German engineering culture was weakest. German engineers designed weapons for ideal conditions, assuming adequate fuel, spare parts, maintenance facilities, and trained crews. American engineers designed weapons for realistic conditions, assuming fuel shortages, limited spare parts, field maintenance under combat stress, and minimally trained crews. The M4A3E8 Sherman that Oberfelwebel Hoffman examined embodied this American design philosophy completely. The designation requires explanation for understanding what made this variant significant. M4 indicated the 4th standardized medium tank design adopted by the United States Army. The Sherman name, unofficial but universally used, honored Civil War General William Tecumseh Sherman. A 3 designated the specific hull variant using welded construction rather than cast hull sections, and critically, indicating the power plant used. The A3 variant was powered by the Ford GAA V8 engine, distinguishing it from earlier Shermans using radial aircraft engines or other automotive power plants. E8 indicated the 8th major engineering change package applied to the M4 design. The E8 package introduced horizontal volute spring suspension, replacing the earlier vertical volute spring suspension that had characterized Sherman designs since 1942. This suspension improvement provided better cross-country performance, improved crew comfort, reduced track wear, and enhanced gunnery stability while moving. The E8 package also included wider tracks, 23 inches compared to 16.5 inches on earlier Shermans, reducing ground pressure and improving mobility in soft terrain. The combination of Ford GAA engine and horizontal volute spring suspension created what American tankers considered the finest Sherman variant produced during World War II. Production of the M4A3E8 began in March 1944 at the Fisher Tank Arsenal in Grand Blanc, Michigan, and at the Chrysler Detroit Tank Arsenal. By March 1945, approximately 4,000 M4A3E8 tanks had been manufactured. The variant was entering service in increasing numbers throughout American armored divisions in Europe, gradually replacing earlier Sherman models, as those older vehicles were destroyed or wore out. German intelligence had tracked Sherman evolution throughout the war, with varying degrees of accuracy. Reports from 1942 described the Sherman as adequately armed and armoured but vulnerable to German anti-tank weapons. By 1943, intelligence assessments acknowledged that Shermans appeared in vast numbers that overwhelmed German tactical superiority through sheer quantity. 1944 reports noted improved Sherman variants with better guns, specifically the 76mm M1 gun, replacing the older 75mm M3 gun. But German intelligence focused primarily on armament and armour, the traditional metrics by which tank effectiveness was measured. Mechanical reliability, ease of maintenance, fuel efficiency, and industrial production methods received less attention. These were precisely the characteristics where American tanks excelled, and German tanks failed. The specific M4A3E8, captured near Remagen, had been knocked out during a local German counterattack on March 17th. The tank belonged to Company B, 33rd Armoured Regiment, 3rd Armoured Division. American forces advancing eastward from the Remagen bridgehead had encountered determined German resistance from elements of the 11th Panzer Division. During the engagement, this particular Sherman had been hit by a Panzerfaust anti-tank rocket that penetrated the right side hull, wounding 2 crew members and setting off ammunition stored in ready racks. The crew had bailed out successfully, abandoning the burning tank. German infantry secured the position temporarily and extinguished the fire before it destroyed the vehicle completely. The damage, while significant, proved repairable. The Panzerfaust had penetrated the hull, but had not destroyed the engine, transmission, or suspension components. German recovery teams, working under cover of darkness, and frequent Allied artillery fire, towed the damaged Sherman to a field workshop 3 kilometers behind the front lines. The workshop, established in a barn complex near the village of Honnef, served the maintenance company of 3rd Panzer Division. By March 1945, this maintenance company possessed more experience repairing Allied vehicles than German ones. Spare parts for German tanks had become nearly unobtainable, but captured American equipment provided an alternative mobility source. Several American trucks and half-tracks had been pressed into German service after minor repairs. The captured Sherman represented something different, not a logistics vehicle but a combat tank potentially returnable to action. Major Ernst Richter, commanding the maintenance company, recognized immediately that repairing the Sherman for combat use was impossible. His company lacked the specialized knowledge, tools, and parts required, but examining it thoroughly could provide valuable intelligence. Richter had served with panzer formations since Poland in 1939. He had fought in France, Russia, and now Germany itself. He had watched German armour superiority erode gradually, then catastrophically as the war progressed. He understood, though he would never state it officially, that German tanks were losing not because of inferior courage or tactics, but because of systemic failures in production, logistics, and strategic planning. Examining a captured enemy tank might reveal principles that German engineers had overlooked. Richter assigned Oberfelwebel Karl Hoffman to lead the examination. Hoffman had worked as an automotive mechanic in Munich before the war. He had trained on Panzer III and Panzer IV maintenance at the Panzer School at Wunsdorf in 1940. He had served with maintenance units on the Eastern Front from 1941 through 1943, repairing tanks under conditions ranging from summer heat to winter, cold that froze lubricants solid. He had transferred west in 1944 and had spent the last year struggling to keep decrepit German armour operational, despite absent spare parts and vanishing fuel supplies. Hoffman brought skills and experience that few German soldiers still possessed in March 1945. He understood tanks mechanically and operationally. The examination began on the morning of March 19th with Hoffman and 3 enlisted mechanics systematically documenting the captured Sherman. They measured dimensions, photographed components, and sketched mechanical systems. The Sherman's exterior dimensions proved compact compared to German medium and heavy tanks. Combat weight was recorded as approximately 31 metric tons, significantly lighter than the Panther medium tank at 45 tons, or the Tiger heavy tank at 57 tons. Length with gun forward measured 24.8 feet, shorter than the Panther's 29.3 feet. Width measured 10.7 feet, narrower than the Panther's 11.2 feet. Height measured 9 feet, lower than the Panther's 9.8 feet. These dimensions immediately indicated different design priorities. German tanks emphasized armor, thickness, and gun power, accepting increased weight and size. American tanks emphasized mobility and production efficiency, accepting reduced armor protection in exchange for lighter weight and smaller size. The armor protection measurements confirmed German intelligence assessments. Frontal hull armor measured 63.5 millimeters at 47 degrees from vertical. When calculated for effective thickness against perpendicular projectile impact, this provided protection equivalent to approximately 92 millimeters of vertical armor. Turret frontal armor measured 76 millimeters, mounted vertically without significant sloping. Side hull armor measured 38 millimeters, adequate against small arms and shell fragments but vulnerable to all German tank guns and anti-tank weapons. These armor values placed the Sherman well below German medium and heavy tanks in protection. The Panther's frontal hull armor of 80 millimeters, sloped at 55 degrees, provided protection equivalent to approximately 140 millimeters vertical. The Tiger's 100 millimeter vertical frontal armor exceeded Sherman protection by substantial margins. German tankers knew that Panthers and Tigers could engage Shermans frontally with near impunity, while Sherman guns struggled to penetrate German heavy armor, except at close range or from favorable angles. This armor disparity had created the widespread German belief that American tanks were technically inferior. The armament examination provided additional apparent confirmation of German superiority. This particular M4A3E8 mounted the 76mm M1A2 gun. The improved American tank gun, introduced in 1944 to address inadequacies of the earlier 75mm weapon. Hoffman's team measured the gun's characteristics carefully. Barrel length of 52 calibers meant the barrel was 52 times the bore diameter, providing good velocity but less than German designs. The Panther's 75mm KAK-42 gun featured 70 calibers of barrel length. The Tiger's 88mm KAK-36 gun featured 56 calibers of length. Longer barrels generally provided higher muzzle velocities, improving armor penetration and accuracy at range. Ammunition examination revealed that American armor-piercing rounds achieved respectable but not exceptional penetration. At 1,000 meters range, the 76mm M1 gun could penetrate approximately 110 millimeters of vertical armor, adequate against Panzer IVs and most German medium tanks, but insufficient against Panther frontal armor. At the same range, the Panther's gun could penetrate approximately 140 millimeters, sufficient to defeat any Allied tank frontally. This penetration differential meant that Panthers could destroy Shermans at ranges where Sherman fire remained ineffective against Panther armor. German tankers had exploited this advantage countless times, but Hoffman noticed something unexpected in the turret design. The gun mounting, recoil mechanism and traverse system appeared remarkably sophisticated. The turret traverse mechanism, driven by hydraulic power with manual backup, rotated the turret 360 degrees in 15 seconds using power traverse. German tanks used manual traverse exclusively. Traverse speeds varied with crew strength and fatigue, but typically required 40 to 60 seconds for full turret rotation under combat stress. The American hydraulic traverse gave Sherman crews significant advantages in engagement speed. They could track moving targets more easily, respond faster to threats from unexpected directions, and maintain accurate aim while traversing. This technological advantage partially offset the Sherman's disadvantages in armor and gun penetration. Hoffman made careful notes about the turret traverse system, recognizing it as evidence that American engineering was more sophisticated than German propaganda acknowledged. The suspension examination revealed the horizontal volute spring system that defined the E8 variant. This suspension used paired road wheels mounted on horizontal volute springs, replacing the earlier vertical volute spring bogies. The new suspension provided several advantages. Better weight distribution reduced ground pressure despite the tank's 31-ton weight. Improved shock absorption enhanced crew comfort during cross-country movement. Reduced track wear extended track life between replacements. Enhanced stability improved gunnery accuracy while moving. Hoffman and his mechanics marveled at the suspension's robust construction. Components appeared overbuilt for the stresses they would encounter. Maintenance access was excellent, with critical components easily reachable without extensive disassembly. Replacement of road wheels or springs could be accomplished quickly by trained crews using standard tools. The contrast with German designs was stark. Panther and Tiger tanks used interleaved road wheel arrangements that provided superior weight distribution but required extensive disassembly to replace inner wheels. A simple wheel change on a Panther could consume an entire day. The same repair on this Sherman would require perhaps 1 hour. For armies operating under field conditions with limited time and resources, this maintainability difference had enormous operational consequences. But the examination that would truly shock Hoffman and his team began when they accessed the engine compartment. Opening the rear hull plates revealed the Ford GAA V8 engine in remarkable condition, despite the fire damage that had knocked out this tank. The engine appeared surprisingly compact for a 500-horsepower power plant. The V8 configuration placed cylinders in 2 banks at 90-degree angle, creating a relatively short and narrow engine package. Total displacement measured 18 litres, large by automotive standards but modest compared to the Maybach engines powering German tanks. The Panther's Maybach HL230 displaced 23 litres. The Tiger's Maybach HL210 and later HL230 also displaced 23 litres. Yet this 18-litre Ford engine produced 500 horsepower, matching or exceeding the output of much larger German engines. Hoffman immediately recognized the significance. This was not a purpose-built tank engine. This was an adapted automotive engine, developed from Ford's commercial truck and industrial power plant designs. The engineering implications stunned him. German engineers had designed specialized tank engines from the ground up, creating complex power plants optimized for armored vehicle applications. These engines delivered impressive peak performance but proved fragile, difficult to maintain, and impossible to produce in adequate quantities as the war progressed. American engineers had adapted existing automotive engines, accepting some performance compromises in exchange for simpler production, better reliability, and easier maintenance. The Ford GAA represented this philosophy perfectly. Development of the GAA engine began in 1941 when the United States Army requested a liquid-cooled engine for tank applications. Ford engineers adapted their existing truck engine designs, creating a V8 specifically for the Sherman tank program. The engine entered production in 1942. By 1945, tens of thousands had been manufactured. The GAA used an aluminum alloy block and heads, reducing weight significantly compared to cast-iron construction. This aluminum construction was sophisticated. Metallurgy for 1942, indicating American industrial capabilities that German propaganda consistently underestimated. The engine featured overhead valves, dual downdraft carburetors, and a sophisticated cooling system designed for sustained high-power operation. Maximum power output of 500 horsepower occurred at 2,600 revolutions per minute. Normal operational output was 450 horsepower at 2,400 RPM, providing reliable power for sustained operations while extending engine life. This power output gave the 31-ton M4A3E8 a power-to-weight ratio of approximately 16 horsepower per ton, comparable to or exceeding German medium tanks. The Panther's ratio was approximately 15.6 horsepower per ton. The key difference lay not in raw power, but in reliability and fuel efficiency. Hoffman spent hours examining the GAA engine's construction. He noted the quality of machining, the precision of tolerances, and the sophistication of design details. This was not crude mass production. This was precision engineering adapted for large-scale manufacturing. Every component showed evidence of careful design to balance performance with producibility. Gaskets used composite materials that sealed reliably without requiring perfect surface finishes. Fasteners used standardized threads and sizes, simplifying assembly and repair. The oil system incorporated full-flow filtration, protecting internal components from contamination that would cause premature wear. The cooling system used a radiator sized for sustained high-power operation, preventing the overheating problems that plagued German tanks. Hoffman compared the Ford engine mentally to the Maybach engines he had maintained for 4 years. The Maybach HL230 was an impressive piece of engineering, 12 cylinders in 60-degree V configuration, sophisticated fuel injection, precisely machined components throughout. But the Maybach required constant maintenance, oil changes every 100 hours of operation, frequent adjustment of fuel injection timing, careful monitoring of coolant temperatures, specialized tools for many maintenance procedures, trained mechanics for any significant repairs, and most critically, the Maybach consumed fuel at rates that made sustained operations impossible when fuel supplies were limited. The Ford GAA appeared designed for different priorities. Maintenance intervals were longer. Adjustment requirements were minimal. Standard automotive tools sufficed for most repairs. The engine could tolerate rougher handling and less precise maintenance, and fuel consumption, while not precisely documented in the hasty examination, appeared significantly lower than comparable German engines. On March 20th, the second day of examination, Hoffman's team attempted to start the captured Sherman's engine. The fire damage had destroyed electrical wiring and damaged the fuel system, but the engine itself appeared intact. After jury-rigging temporary fuel lines and repairing essential electrical connections, they attempted ignition. To Hoffman's surprise, the engine started on the second attempt. It ran roughly due to improvised repairs, but it ran. The sound was distinctive, a deep rumble very different from the higher-pitched note of German tank engines. More importantly, the engine ran smoothly at idle and responded cleanly to throttle inputs. There were no unusual vibrations, no concerning mechanical noises, no signs of internal damage from the combat hit and subsequent fire. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The resilience impressed Hoffman profoundly. German tank engines, if exposed to fire and subsequent weeks of sitting dormant, typically required extensive rebuild before running again. This American engine started and ran despite significant abuse. The implications for operational availability were clear. Tanks that could return to service quickly after damage had enormous advantage over tanks requiring lengthy repairs. Hoffman authorized a brief test drive around the field. One of his mechanics, who had briefly trained on captured American vehicles, took the driver's position. The Sherman moved smoothly, despite battle damage and improvised repairs. The transmission shifted cleanly through its 5 forward gears. The steering, using controlled differential braking of tracks, responded precisely to driver inputs. Acceleration was brisk, particularly in lower gears. The top speed, limited by field conditions and mechanical uncertainties, still reached approximately 30 km per hour during the brief test. Most significantly, the ride quality was dramatically better than German tanks. The horizontal volute spring suspension absorbed terrain irregularities smoothly. The tank remained relatively stable even over rough ground. Cruise stations showed evidence of careful ergonomic design, with controls positioned logically and visibility adequate from all positions. After 20 minutes of cautious maneuvering, they returned the Sherman to the examination area and shut down the engine. Hoffman gathered his notes and prepared his preliminary report for Major Richter. The report's conclusions would have been considered defeatist or treasonous if stated too explicitly in March 1945 Germany. But Hoffman could not ignore what he had observed. The American Sherman tank was not crude mass-produced junk as German propaganda claimed. It was sophisticated engineering adapted for mass production, sustained operations, and ease of maintenance. In those characteristics, it was superior to German tanks, perhaps decisively so. The Ford GAA engine exemplified a design philosophy fundamentally different from German approaches. Instead of maximizing peak performance at any cost, American engineers optimized for sustained reliable performance under field conditions. Instead of requiring specialized manufacturing facilities, American designs used adapted automotive technology producible in existing factories. Instead of demanding highly trained maintenance personnel, American designs simplified maintenance to levels achievable by minimally trained crews. These choices, derided by German engineers as evidence of technical inferiority, actually represented sophisticated systems engineering that German military culture struggled to understand or value. Hoffman's report, submitted to Major Richter on March 21st, documented technical specifications, construction details, and design features observed during the examination. The report concluded with observations that Hoffman knew would prove controversial. The captured Sherman tank demonstrates engineering approach fundamentally different from German design philosophy. American engineers prioritize reliability over maximum performance, maintainability over sophistication, and production efficiency over individual excellence. Results in vehicle that is adequate in all characteristics rather than excellent in specific parameters. But adequacy sustained across thousands of vehicles over years of operations defeats excellence that cannot be maintained. The Ford GAA engine represents particular achievement. 500 horsepower from 18 litres displacement indicates sophisticated engineering. Aluminum construction reduces weight while maintaining strength. Design details suggest this engine can be maintained under field conditions by personnel with standard automotive training. Fuel consumption appears significantly lower than comparable German engines, though precise measurement was not possible during examination. Recommend immediate technical intelligence report for submission to higher authorities. American tank design philosophy appears more appropriate for sustained industrial warfare than German emphasis on individual technical superiority. Major Richter read the report carefully. He understood immediately that Hoffman's conclusions, though technically accurate, could not be submitted through official channels without significant sanitization, suggesting that American engineering might be superior to German engineering in any respect contradicted fundamental premises of Nazi ideology. But Richter also understood that the observations were valid and important. He filed the report in his company records and prepared a much shorter, more politically acceptable summary for division headquarters. That sanitized report simply documented that a captured American tank had been examined, noting specifications without drawing broader conclusions. The complete report, with Hoffman's detailed observations and controversial conclusions, remained in company files. Those files were captured by American forces when 3rd Panzer Division surrendered in late April 1945. Hoffman's report eventually reached American intelligence officers, who found his observations remarkably perceptive. The report confirmed what American engineers knew but Germans apparently had not fully understood, that the Sherman's greatest strengths lay not in armor or firepower, but in reliability, maintainability, and sustainable production. The story of Hoffman's examination represents one small window into broader patterns that characterized the final year of war in Europe. German forces operated technically sophisticated equipment that their logistics system could not adequately support. American forces operated adequate equipment that their logistics system sustained abundantly. In sustained operations across vast distances, adequacy sustained defeats, excellence that cannot be maintained. The Ford GAA engine exemplified this principle. It was not the most powerful tank engine per litre of displacement. German engines achieved higher specific output. It was not the most sophisticated. German fuel injection systems were technically more advanced than American carburetors. But the Ford engine was reliable, maintainable, fuel-efficient, and producible in quantities that German industry could not match. Those characteristics, dismissed by German engineers as evidence of crude American mass production, actually represented sophisticated understanding of industrial warfare's requirements. Wars are not won by the best tanks. They are won by adequate tanks present in overwhelming numbers, sustained by logistics that can keep them operational across extended campaigns. The M4A3E8 Sherman embodied that understanding completely. Its Ford GAA engine, adapted from commercial automotive designs rather than purpose-built for military applications, represented engineering philosophy that valued sustainability over peak performance. That philosophy, alien to German military culture, proved decisive. By March 1945, the strategic situation made individual weapon comparisons increasingly irrelevant. Germany faced enemies on all fronts who possessed not only superior numbers but also superior logistics, superior industrial production, and superior operational sustainability. German tanks might win individual engagements through superior armor and firepower, but German forces could not sustain operations because their technically excellent weapons consumed resources that no longer existed in adequate quantities. The examination of a single captured Sherman could not change Germany's strategic situation, but it revealed to at least some German soldiers that their understanding of American technical capabilities had been fundamentally flawed. American engineers had not produced crude weapons through inability to match German sophistication. They had produced sustainable weapons through clear understanding that industrial warfare rewarded reliability and producibility over individual excellence. This was a lesson Germany learned too late, if German military leadership truly learned it at all. The broader context of Sherman development reveals why the Ford GA engine became central to American tank production strategy. When the United States entered World War II in December 1941, American tank design lagged behind European standards. The M3 Grant medium tank, rushed into production in 1941, mounted its main gun in a hull sponson rather than a rotating turret, a configuration obsolete by contemporary standards. The M4 Sherman, entering production in February 1942, represented a dramatic improvement with its fully rotating turret, sloped frontal armor, and adequate firepower for early war conditions. But the Sherman program faced immediate challenges in engine selection. The original M4 design used the Continental R975 radial aircraft engine, producing 400 horsepower. This engine, reliable and available in quantity from aircraft production, powered the majority of early Shermans. However, American military planners recognized that relying on aircraft engines for tank production created competition between aviation and armored force requirements. Alternative power plants needed development. Chrysler developed a multi-bank engine using 5 commercial truck engines connected to a common crankshaft. General Motors developed diesel engines adapted from their locomotive division, and Ford developed the GAA, a purpose-designed tank engine based on their commercial V8 architecture. The Ford GAA entered production in 1942 at Ford's River Rouge complex in Dearborn, Michigan. The same facility produced truck engines, aircraft engines, and other military equipment. This shared production infrastructure exemplified American industrial philosophy. Rather than building specialized facilities for each weapon system, American industry adapted existing factories, leveraged common components across multiple products, and achieved economies of scale that German industry, with its emphasis on specialized production, could not match. By 1945, Ford had produced over 50,000 GAA engines. These engines powered not only M4A3 Shermans but also M26 Pershing heavy tanks entering service in the war's final months. The production volume exceeded total German tank engine production across all types during the same period. More importantly, the production was sustained and reliable. Ford delivered engines on predictable schedules, meeting or exceeding contracted quantities. German tank engine production, by contrast, suffered constant disruptions from Allied bombing, raw material shortages, and increasingly chaotic transportation networks. Maybach could not deliver engines consistently even when production facilities remained operational because components came from multiple suppliers across Germany, and the transportation system connecting them disintegrated progressively throughout 1944 and 1945. The fuel efficiency differential between American and German tank engines had enormous strategic consequences that became increasingly apparent as the war progressed. The Ford GAA consumed approximately 0.8 gallons of fuel per mile under typical road conditions. The Maybach HL, 230 inches, the Panther consumed approximately 1.95 gallons per mile under similar conditions. The Tiger's fuel consumption was even worse, reaching 2.8 gallons per mile on roads. These differences, individually modest, compounded across hundreds of tanks and thousands of miles into overwhelming logistical advantages. An American armored division with 200 Shermans conducting a 100-mile road march consumed approximately 16,000 gallons of fuel for its tanks alone. A German Panzer division with 100 Panthers conducting the same march consumed approximately 19,500 gallons, despite fielding half as many tanks. When including all division, vehicles, trucks, half-tracks, reconnaissance vehicles, artillery prime movers, American divisions remained more fuel-efficient per unit of combat power delivered. This fuel efficiency advantage became decisive during mobile operations in summer and fall 1944. American armored divisions advancing across France after the Normandy breakout conducted operations spanning hundreds of miles. Supply lines stretched but remained functional because fuel requirements, while enormous in absolute terms, remained within sustainable limits given American logistics capabilities. German Panzer divisions attempting to respond to these American offensives found themselves immobilized repeatedly by fuel shortages. Even when fuel existed in rear area depots, the transportation network could not deliver it forward fast enough to sustain mobile operations. Panthers and Tigers sat immobilized not because they were mechanically unreliable, though they were, but because their operational fuel consumption exceeded what German logistics could provide under combat conditions, with Allied air forces interdicting supply lines. The maintenance differential compounded the fuel consumption advantage. Sherman tanks required approximately 10 man-hours of maintenance per 10 hours of operation under typical conditions. This maintenance, mostly routine servicing like oil changes, filter replacements, and track adjustment, could be performed by crew members or unit-level mechanics using standard tools. German tanks required approximately 20 to 30 man-hours of maintenance per 10 hours of operation. Much of this maintenance required specialized tools, trained technicians, and replacement parts that were increasingly unavailable as German supply systems collapsed. A Sherman that threw a track could have it repaired and be operational again within 2 hours by the crew alone, using tools carried on the vehicle. A Panther that threw a track required recovery to battalion level, maintenance, specialized track repair tools, and typically 4 to 8 hours of work by trained mechanics. The time differential meant that Sherman-equipped units spent more time operational and less time awaiting maintenance. The operational availability rates reflected these maintenance differences with mathematical precision. American armored divisions typically maintained 70 to 80% of authorized tank strength in operational condition at any given time. German Panzer divisions in 1944 and early 1945 averaged 40 to 55% operational availability for their Panthers, and even lower for Tigers. This availability differential, approximately 30 percentage points favoring American forces, meant that paper strength comparisons were misleading. A German Panzer division authorized 100 Panthers might field 50 operational tanks on average. An American armored division authorized 200 Shermans might field 160 operational tanks. The 3-to-1 numerical advantage in actual battlefield presence overwhelmed German tactical superiority in individual tank engagements. The production cost differential revealed another dimension of American advantage. A Ford GAA engine cost approximately $1,000 to manufacture in 1944, including materials, labor, and allocated overhead. The complete M4A3E8 Sherman cost approximately $45,000 in the same accounting framework. A Maybach HL 230 engine cost approximately 3,500 Reichsmarks to manufacture, roughly $1,400 at official exchange rates, though black market rates were far less favorable to the Reichsmark. The complete Panther tank cost approximately 117,000 Reichsmarks without armament, approximately $47,000 at official rates. In direct cost comparison, Panthers cost marginally more than Shermans, but not prohibitively so. The critical difference lay in production time and labor requirements. A Sherman required approximately 10,000 man-hours to produce in established factories operating at full efficiency by 1944. A Panther required approximately 15,000 man-hours, 50% more labor for each unit. American factories used advanced production techniques, including extensive subassembly, standardized components across variants, and progressive assembly methods minimizing skilled labor requirements. German factories relied more heavily on skilled craftsmen, fitting components that were less precisely standardized, increasing production time and costs. American production peaked at over 2,000 Shermans per month during mid-1944. German Panther production peaked at approximately 380 units per month, less than one-fifth of American output, despite Germany dedicating proportionally more industrial capacity to tank production. The Sherman won the war while the Panther lost it, fundamentally because specifications written on paper mattered less than presence on the battlefield. The principle that determined victory was not which tank had better armor or firepower, but which tank was actually present and operational when needed, sustained by logistics that could keep it fueled, maintained, and combat-ready across extended campaigns in hostile territory. The human dimension of this technological competition emerges from the scattered records and accounts that survived. German tankers who encountered Shermans in combat typically reported tactical superiority. The Panther could engage at longer ranges. Its armor resisted Sherman fire more effectively than Sherman armor resisted Panther fire. In static engagements at medium to long range, German tanks possessed decisive advantages, but actual combat rarely conformed to these ideal conditions. Shermans appeared in overwhelming numbers. They maneuvered aggressively, using mobility to offset armor disadvantages. They called upon artillery and air support that German forces increasingly lacked, and critically, destroyed Shermans were replaced within days or weeks, while destroyed Panthers might never be replaced at all. German tankers learned through experience that killing 3 or 4 Shermans meant nothing strategically when 5 or 6 more appeared the next day. This psychological burden, knowing that tactical success could not achieve strategic effect, corroded German morale throughout the war's final year. American tankers who captured German tanks universally praised their armor and firepower, while noting their mechanical fragility and logistical demands. After-action reports from American units that evaluated captured Panthers and Tigers consistently emphasized that German tanks required excessive maintenance, consumed fuel at unsustainable rates, and broke down frequently under field conditions. These reports concluded that American tanks, despite inferior armor and firepower, were superior weapons overall because they could be sustained in combat operations. The philosophical divide between German and American approaches to military technology extended far beyond tanks. German small arms were magnificently engineered but expensive and slow to produce. The MP-40 submachine gun required approximately 10 hours of skilled machinist time to manufacture. The American M3 grease gun required less than 3 hours of semi-skilled labor. Both weapons fired similar caliber ammunition at similar rates. The American weapon was cruder, uglier, and vastly more practical for mass production. German artillery emphasized precision and range at the expense of quantity. American artillery emphasized rapid production, abundant ammunition supply, and responsive fire direction systems. German doctrine called for carefully planned artillery concentrations delivered at predetermined times. American doctrine emphasized flexibility and rapid response to forward observer requests. American artillery could deliver battalion-level fire within 5 minutes of request. This responsiveness proved more valuable tactically than the superior range of German guns. The pattern repeated across virtually every category of military equipment. German engineers designed for ideal conditions. American engineers designed for realistic conditions. German industry produced sophisticated weapons that logistics could not sustain. American industry produced adequate weapons that logistics sustained abundantly. In extended industrial warfare across vast distances, adequacy sustained defeated excellence that could not be maintained. This was the fundamental lesson that the examination of captured Sherman tanks taught German soldiers who were capable of learning it. The fate of Oberfelwebel Karl Hoffman and his examination team illustrates the chaos of Germany's final collapse. 3rd Panzer Division surrendered to American forces on April 26, 1945, near Nuremberg. Division records, including Hoffman's report on the captured Sherman, were secured by American intelligence teams. Hoffman himself survived the war and returned to Munich, where he resumed work as an automotive mechanic. In a brief interview conducted by American military government officials in July 1945, Hoffman stated that examining the American Sherman had convinced him that German technical superiority was largely propaganda. The Ford engine, he noted, represented sophisticated engineering adapted for practical application rather than theoretical excellence. This was a lesson German industry had failed to learn. Major Ernst Richter also survived and provided similar observations during Allied interrogations. His testimony contributed to comprehensive post-war studies of German armored forces that analyzed why technically superior German tanks failed to prevent strategic defeat. These studies, conducted by British and American intelligence services through 1946 and 1947, concluded that German tank development emphasized wrong priorities. Armor protection and gunpowder received disproportionate attention, while reliability, maintainability, fuel efficiency, and production efficiency received insufficient emphasis. The studies recommended that future Allied tank development maintain American emphasis on operational sustainability, while incorporating technological advances where feasible without compromising reliability. This philosophy informed development of every major American armored vehicle designed after World War II, from the M48 Patton through the M60 series to the M1 Abrams. The principle that the best weapon is one that is actually available when needed, rather than one with the most impressive specifications, became foundational to American military procurement. The M4A3E8 Sherman remained in American service through the Korean War, where it proved adequate against North Korean T-34, 85 tanks, and effective in infantry support roles. Several thousand M4A3E8s were transferred to Allied nations under military assistance programs and served with various armies through the 1970s. The last combat use of Shermans occurred during the 1982 Lebanon War, over 40 years after the type entered production. This longevity reflected the Sherman's fundamental soundness as a design. It was adequate in all characteristics, reliable in service, maintainable under field conditions, and adaptable to various roles. These virtues, derided by critics who focused narrowly on armor and firepower comparisons, proved more valuable than technical excellence that could not be sustained. The Ford GAA engine, the component that most impressed German examiners, continued in production through 1945, with over 53,000 units manufactured. Post-war, surplus GAA engines found civilian applications in industrial equipment, marine propulsion, and even drag racing. Hot rodders discovered that the GAA's aluminum construction and robust design made it ideal for high-performance applications. Modified GAA engines producing over 1,000 horsepower appeared at drag strips in the 1950s and 60s. This civilian adaptability further demonstrated the engine's fundamental excellence as a design. It was not merely a military expedient, but a genuinely sophisticated power plant suitable for demanding applications far beyond its original purpose. The comparative legacy of German and American tank development extends to present-day military procurement and defense industrial policy. Modern defense acquisition emphasizes reliability, maintainability, and logistical sustainability as requirements equal to combat performance. Durability testing is mandatory before production approval. Maintenance procedures are evaluated as rigorously as combat capability. Supply chain sustainability factors into procurement decisions from the beginning. These practices, now standard throughout Western militaries, originated from lessons learned studying why German tanks failed strategically despite succeeding tactically. Engineering schools continue using the Panzer versus Sherman comparison as case studies in systems engineering and industrial design. The case studies examine requirements definition, design trade-offs, production engineering, logistics integration, and life cycle cost analysis. Students learn that optimizing individual specifications, without considering system-level requirements, produces weapons that fail operationally, despite impressive technical characteristics. This lesson applies far beyond military equipment to commercial products, infrastructure systems, and any domain where reliability and sustainability matter as much as peak performance. The mathematical reality that condemned German armored forces emerges clearly from production and operational statistics. Germany produced approximately 6,000 Panthers and 1,300 Tigers between 1943 and 1945. Operational availability averaged 40 to 55%. This meant that Germany fielded approximately 3,000 operational Panthers and 700 operational Tigers, on average across all fronts. The United States produced 49,000 Shermans of all variants between 1942 and 1945. Operational availability averaged 70 to 80%. This meant that the United States fielded approximately 35,000 operational Shermans on average, globally deployed. The numerical advantage exceeded 10 to 1 in actual battlefield presence, despite German tanks' tactical superiority in individual engagements. This numerical disparity, combined with American advantages in artillery, air power, logistics, and industrial production, made German defeat mathematically certain regardless of tactical skill or soldier quality. The examination of a captured M4A3E8 Sherman by German maintenance personnel in March 1945 revealed truths that German military leadership had refused to acknowledge throughout the war. American engineering was not crude or inferior. It was sophisticated engineering adapted for different priorities than German designs emphasized. American industry had not produced millions of weapons through inability to match German quality. American industry had produced millions of weapons through clear understanding that industrial warfare rewarded sustainable mass production over individual excellence. American military doctrine had not emphasized logistics and sustainability from weakness. American doctrine emphasized these factors from strength, from recognition that modern warfare was won by systems that sustained operations over extended time and distance. The Ford GAA engine, the component that most impressed German examiners, symbolized this American approach. It was not the most powerful engine per liter of displacement. It was not the most sophisticated technically, but it was reliable, maintainable, fuel-efficient, and producible in quantities that shaped strategic outcomes. Those characteristics, dismissed as evidence of inferior engineering by German military culture, actually represented superior understanding of what industrial warfare required. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The tank that German propagandists mocked as crude mass-production junk proved to be sophisticated systems engineering that won the war. The engine that German mechanics examined with surprise and respect in a muddy field outside Remagen represented a design philosophy that valued sustainable adequacy over unsustainable excellence. In the final accounting, that philosophy proved decisive. Wars are won not by the best weapons, but by adequate weapons present in overwhelming numbers, sustained by logistics that keep them operational across extended campaigns in hostile territory. The M4A3E8 Sherman embodied that understanding completely. Its Ford GAA engine, adapted from commercial designs rather than purpose-built for military service, represented engineering wisdom that German culture struggled to comprehend or value. That wisdom, purchased through careful study of what actually worked under field conditions rather than what looked impressive on paper, shaped American military procurement for decades after World War II. The lessons remain relevant today, whenever sophisticated technology must be sustained in demanding environments over extended periods. The Sherman was never the best tank of World War II by any single specification, but it was the best tank for winning the war, which is the only specification that ultimately mattered. The German tankers who examined it in March 1945, if they were honest with themselves, recognized that truth. Their recognition came too late to change anything, but it validated principles that shaped the post-war world. Adequacy, sustained across time and distance, defeats excellence that cannot be maintained. The 500-horsepower Ford V8 that stunned German mechanics proved that lesson definitively. It powered adequate tanks to victory, while sophisticated German engines powered excellent tanks to defeat. That paradox contains the complete story of armoured warfare in World War II, compressed into 18 litres of displacement and 53,000 units of reliable, sustainable, war-winning American industrial engineering. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.